So in this video, we're going to talk a little bit more about first and second derivatives. In the previous video, we sort of introduced the concepts and sort of talked about some fundamental ideas. And in this video, we're going to just look at some applications, and we're going to slowly begin our transition into the concept of curve sketching, which is a pretty important part of differential calculus. All right, so let's get started. So here's a little problem to begin with. You're going on a holiday, and you load your car, and you begin driving at a velocity of plus 9 meters per second. Yeah, and then you hit the gas, and you gain a constant acceleration of 1 meter per second squared. And I know you may be thrown off by the units and the plus signs, but that's just following physics conventions. For the purpose of a calculus class, you don't really need to worry about those. But what do we mean by velocity and acceleration again? We talked about them in the previous video, but let's just do a quick recap and make sure we understand what these things mean. So we start at position, right? S of t is position. And in this case, it's position from your origin or from your house, right? Now, if we take a first derivative of position, if we say s prime of t, then we have velocity, or v of t. And this represents, in terms of position, it represents an instantaneous rate of change of position. Okay? So it represents an instantaneous rate of change of position. Now, what about acceleration though? Well, acceleration, if you remember, is the second derivative of position, but it's not just that, it's also the first derivative of velocity, v prime of t, and this represents two things. You could think of it as the instantaneous rate of change of that, but what I'm going to say is it's the instantaneous rate of change of velocity. So we have a rate of change of velocity. Right? So that's where these things are coming from. That's what these ideas are all about. Right? Now, let's go ahead and dissect the problem and see what these numbers actually mean. All right. So this velocity right here, what do you notice about it? It's a positive number, right? This velocity is a positive number. So at time 0, or v of v naught is positive. We don't care so much about what exactly that number is for now, but we know that's a positive number, right? So if it's positive, then what do we know about position? What does that tell us about position? So I'll give you a second there. Just try to fill in the blank and pause the video if you need to. Well, position is increasing, right? It's going to be increasing. At that instant of time that's t equals 0, our position is increasing, right? And now we have another piece of information though. We have a position, we have acceleration as well. And acceleration it's constant and it's positive. So it's always positive, right? So what should that tell you about velocity? So what does that tell you about velocity? Again, take a second and see if you can figure that out. Well, it should also tell you that velocity is increasing, right? Right? So our velocity is increasing. So again, velocity, recall, is our instantaneous rate of change of position, right? It's our first derivative of position. And as we can see, because we have an acceleration that's positive, or an acceleration, let me remind you, is the first derivative of velocity, then we can make the inference that the velocity is increasing, right? So this is a pretty important information, and we're going to talk about it a little bit more. All right, so let's go ahead and graph velocity versus time. Now you should have the skills to be able to do this by yourself. You're given all the information that you need to, but nonetheless, let's do this together. So we're given our initial velocity, right? So that's a y-intercept. So if we set up our plot to go by 5s, right? We can go 10 and 15. We can go ahead and set our y-intercept somewhere around there. And that's going to be initial velocity of 9 meters per second. Now, what sort of function would this look like? Given So now we're given another. So now we're given another piece of information. We're given an acceleration, right? And an acceleration, as we've talked about, represents the instantaneous rate of change of velocity. It also represents one other thing, though. And this again goes back to all the things I've been talking about since the beginning of this series. So acceleration represents the instantaneous change of velocity, yes, but it also represents the slope of the tangent line of velocity. Okay, so that represents the slope of the tangent line of velocity. So at any given point, any given time, you can use that function to get the slope of the velocity function. Now, because that's a constant slope, we can infer that this is going to be a linear function, right? Because linear functions have constant slopes. Okay, so that's something we can use right there. So let's go ahead and draw this graph. So at t equals 0, we have that. At t equals 1 second, our velocity would be it would be 10, right? So we'd have another point up there. And you could actually just draw the line using these 2 points right away. You don't even need any more points. So you could, right? And this would be v of t. Okay, that's what this would look like. Now let's make some inferences about what's going on here. Okay, so what is happening to v of t over time? V of t is, just take a second there and fill in the blank. It's increasing, right? It's increasing. And this is something we talked about in the previous slide as well. Velocity is increasing, but here you can clearly see that because of this acceleration, let's make sure we highlight that. Because of acceleration, the velocity is increasing. All right, that's something we should make clear. Now here's the second little fun part. How does this relate to s of t? That's the question I want to ask you. So take a second, pause the video, just think about that. How is the fact that the velocity is increasing affect position? Think about it for a second. All right, so now let's go ahead and just think about some things. So remember, velocity is the first derivative of position, right? We've said this like 20 times over the past these few videos. Now, what does this mean? Again, we've said like 300 times. It means that velocity is the instantaneous rate of change of position. However, remember what we said over here. Acceleration is the slope of the tangent line of velocity, and acceleration is the first derivative of velocity, right? So therefore, we can use that same logic to say that v of t is the slope, or represents the slope of the tangent line of s of t. Okay, so v of t is the slope of the tangent line of s of t. So here's a little question I have for you. What inference did we make up here? We said that velocity is increasing, right? And the velocity is the slope of the tangent line of s of t. That means that the slope of the tangent line, or I'm just going to use m tan there to abbreviate, of s of t is increasing. Simple commutative logic there. So what this means, let's think about what this might mean there. So at any given instant of time, if we were to just draw a little graph on the side here. So what's happening is that at any given instant of time, the slope of the tangent line is constantly increasing. Right? It's getting steeper and steeper. And we saw examples of this in the graphing derivatives videos, right? We saw examples where when the derivative is increasing or decreasing, the function does something like this. And this is honestly what the whole point of these videos are. Analyzing this behavior is what we're going to talk about now. So we're gonna look at this some more in the next slide, but for now I want you to understand this. Velocity is increasing because of the acceleration, all right? And because velocity is the slope of the tangent line of position, the position function is going to have this kind of interesting behavior, and that is how the second derivative, acceleration, relates to the original function, position. All right, and that's what we're going to look at this real time in the next slide. All right, so now let's go ahead and graph position versus time and really see how everything ties together. Okay, so let's assume we start at the position at the origin, right? We start at a position of 0 at time 0. So at this point of time, what's going to be the slope of the tangent line? Well, it's going to be 5, right? And that's going to be something like this. Actually, let's draw a better scale so that this is not too big. So let's assume we go in 5s, like this. Because the slope of 5 is kind of steep, and so I don't want too steep lines because those would be hard to see. So I'm just going to shorten the scale a little bit. So right now, slope of 5 would look something like that, right? So m equals 5. Okay, now let's look at time 1, right? At this point of time, now suddenly if we picked, let's say it was over there, then the slope of our tangent line is no longer 5, it's going to be 6, so that's going to be ever slightly steeper. Maybe I should draw that better, but it would be ever so slightly steeper. Something like that. M equals 6. Okay. Now let's take another second. So t equals 2. And let's say it's up here somewhere. Then I don't actually know what the position, what values the position function will take on, right? Because I don't have the function for the position, the actual function for position. But that's where, or we don't have the tools to get the function for position. But this again is how we relate this whole topic to curve sketching. We don't even actually have to know the function. We can just use this information to get a good sketch. So at time equals 2, my slope is going to be 7, right? So it's going to be even steeper. I think you'll start to get the idea, right? You're eventually going to have a curve that does something like this. Let's use red. Actually, no, let's use a different color. Let's draw a green curve. So here the slope is going to be like this, and then this, as you can see, the slope is going to get steeper and steeper, and eventually you're going to get something like that. All right. So here's the important point I wanted you to draw from this. Why do we have this curvature? Why do we have this upward curvature like this? That's because, right, because of the constantly increasing tan, right? Because of our constantly increasing tangent line slope, we get that kind of curve like this. Why do we have a constantly increasing tangent line slope? That is because of AFT, which is S double prime of t. So that, ladies and gentlemen, is how the second derivative has an impact on the graph of the first derivative. And that's the major point I wanted to talk about in this video. Now, what do you call this phenomenon, this kind of effect that the second derivative has? Well, this is a concept we call concavity. Okay, this is the name of the concept that we discussed today. How the second derivative affects the graph of the first derivative, how it makes it look like this. That is what we call concavity. So that's it for this video. In the next video, we're going to explore some more intricacies of this and see how this really applies in curve sketching. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time.